We now turn to the scientific roots of this story with Research to Quantum Technology, a session exploring how breakthroughs in single atom control and Rydberg physics have matured into deployable quantum technology. To lead us through this keynote, please welcome Pasqal's co-founder and research director at CNRS, Antoine Browaeys.
Good afternoon, everyone. A real pleasure to see so many people here today. And a big thank to Wazik for having set the stage. And I have to admit that when we started Pasqal 7 years ago now, I was very far from being able to imagine that we would be there today. I mean, at such a scale, having delivered operating machines, this is actually a truly amazing achievement. So indeed, what I would like to do is to go a bit in the past and told you how we made this journey from fundamental research to quantum technologies. And what I mean by quantum technology is essentially what Wazik talked about and the success that you saw in those Pasqal's achievements. So let's try to open one of these machines, this QPU, which is about 2 meters times 3 times 2, something like this. And if you look inside at a very conceptual level, this is what you will find. So you'll find something where you have laser beams, lots of them, a lot of electronics, a lot of softwares to control all of this. And at the core of that, you've got a vacuum chamber, which is this kind of roundish stuff there, where all the laser beams are sent to. And if you zoom in and look inside, you'll find this assembly which looks very bizarre, like a modern art type of culture, where you have wires to create magnetic fields, you've got electrodes to create electric fields to control the atoms, you've got lenses that I will talk to you about in a minute. So what is, at the conceptual level, the working principle of those machines? So essentially, you start with atoms, and these atoms are going to carry the quantum information. So essentially, you take a laser beam, but it's essentially a regular laser beam, the kind of laser beam that people use in presentations. So not today, I don't have any, but you know, a few milliwatts of laser light. You focus this light down to the smallest possible size you can, actually, considering the optics you have, typically a micrometers. And there, it turns out that you can trap one and only one atom. So it means that if the light interacts with these atoms, the place where the intensity is the largest is going to be the trapping place of the atoms. So it's called an optical tweezers, this thing. And the thing which is completely amazing is that you can place one atom and you can see this atom. And you can see this atom the very same way I can see you, just simply because you send lasers on these atoms, and the atoms reflects the light, scatters the light, we say, and you can collect this light on a camera. So in this way, you can see an atom. And these atoms, you can place them in grids, in arrays. So here it's just a square grid of about 200 atoms. And the reason why you can do that is because on the laser beam that you use to create this array, you place what is called a diffraction grating. And most of us have actually diffraction gratings at home. It's just simply the curtains that you have in your living room, for example, and you look at the light which is outside, and you see all these kind of little spots around the main spots, and you can imagine that each of these spots are simply going to be an extra traps where you can trap an atom. So in this way, you can shape almost arbitrarily the geometry of your array. Now you need to encode the information. And the way you encode the information is a bit more subtle, but you encode the information on what are called the electronic states of the atoms. So essentially, if you think of the atom as the nucleus and some electrons around, it turns out that the nucleus and the electrons are a bit like magnets. They are the north pole and south pole. And you can imagine two configurations. Either the north is up for the nucleus and the north is down for the electrons, or vice versa. And that encodes the 0 and the 1, which are at the basis of logic of qubits. The point, which is only true because of quantum mechanics, is the fact that you can place an electron in a superposition, in being in the two states at the same time. So this is called a quantum superposition. It's a bit as if you were taking a coin and you would put it in a superposition of being both head and tails at the same time. But make no mistake, there is no classical analogy. It's a purely quantum phenomena, and you have to live with this fact. It's a rule of nature. Finally, if you want to do a calculation, you need to create gates. So you need to make those qubits interact with each other. And this is done by promoting the electrons to a very high orbit. So essentially, you have the electrons paralleling around the nucleus, and you kick it out in a very large orbit. And there, because the nucleus, which is charged plus, and the electron, which is charged minus, are so far from each other, it acts as a little antenna. And two of these little antennae, because the distance between those two charges is so large, can act extremely strongly, even at micrometers distance. So that's the way we build those 2 qubit gates that are necessary in order to create a circuit. And so another feature of these arrays is that you can locally address by laser beams any atoms in this structure. So in this way, you can make them interact, and even better than that, you can even move the atoms around so that you can bring any atoms in and make it interact with any other atoms. So you just move the atoms, grab it by a moving tweezer in exactly the same way as the moving head in your CD player or DVD player works. And so this is an example where you move, and each time there is a red circle, you make the atoms interact. And in this way, you can make every atoms interacting with any other atoms in the structure and create what is called an all-to-all connectivity, which is actually the strong asset of the neutral base technology. So now that I'm done with the concept, let me show you that actually all this took actually quite a long time to develop, from the basic principle, the conceptual idea, to the realization in the lab, and to the fact that now, today, you can have in a single machine 20 years of development that were performed in the lab. So I will focus on the development mainly done at the Institut Optics, because for a very long time, there were only a few groups around the world working on that, essentially 2, actually, the group of Mark Safman in the US as well. And so it's all started, as Wazik said, around 2000. And it started at the Institut Optics with the work of Philippe Granger, who is the true pioneer of all this, and Georges, who was the first CEO of Pasqal, who was also a co-founder. And we managed that you can trap in this tweezer, in this tightly focused laser beam, only one atom. So that was before I joined. Actually, I joined slightly later. And the first thing that we did after I joined was to demonstrate that indeed you can create a small array. So it was kind of a crappy array. It was the very beginning. But we managed to do in an heroic weekend, I remember that, the trapping of just 5 atoms at the time. 2007, so you see an extra 3 years to be able to demonstrate that actually you can encode quantum information on an atom. So an atom can be made a qubit. And so at the time, same thing, very crappy qubit, but that was the beginning. And the very same years, we also showed, and that was far from being trivial for many people at the time, that you could move the qubit around in the tweezer. So you take the tweezer, encode the qubit, and move the tweezer around up to 1 millimeter, so quite a large distance, and still the coherence, which is to say the quantum superposition, remained stable over this displacement. So this is today at the heart of the technology. And then in 2009, we were able to demonstrate that precisely by doing these Rydberg excitations to highly excited interacting state, we could make 2 qubits interact. And we could even demonstrate that they would generate entanglement, which are those quantum correlations necessary to perform a calculation. And that completely unlocked the field, because essentially that allowed us and others to start implementing these proposals from the early 2000s from the group of Peter Zoller, Michal Lukin, and a few others. Then early on, our interest was, let's try to do the physics with that. And we started to embark on elementary quantum simulations, not necessarily having in mind material science. It was too far ahead at the time. And in 2016, we changed scale. So essentially, up to now, we're just handling a few atoms, 3, 4, 5, or something like this. And in 2016, we showed that we could really scale up. So essentially, we devised a method that allowed to assemble large arrays of tweezers based on the principle that we had demonstrated in 2004. So this is when we created this assembled Eiffel Tower, which is completely useless, obviously, for physics, but which at least showed that you have an arbitrary, ability to place the atoms in space. And then came 2018. And in 2018, actually, pushed by Christophe Jurzac, we came back from the US, and also by Alain, who is kind of the godfathers of all this, we said, well, the technology is probably mature enough that we can envision transferring it to a company. And so that's how Pasqal started at the time. I will give you a few more motivation in a minute, but that's when we started. But still, no one had yet performed a large-scale quantum simulation with this. And this is what we did in the lab in 2021, where we were able to implement a first demonstration of what is called a quantumizing model. It's a bit of a detail, it's not too important, but that's an iconic system, an iconic many-body physics system that could simulate in a regime where at the time no one could calculate exactly what was going on. Since then, numerics have made some progress, but still it's a challenging system to solve. All right. So the motivations behind Pascal. So there were essentially two motivations for Thierry, who is a co-founder as well, working in our group at the Institut d'Optique, and myself. And if you ask each of the founders, probably they have slightly different motivation, but there were two ideas. The first one is that everything we've been developing so far was done in an academic lab with limited funding, especially at the time, with PhD students. So, you know, they stay for 3 years, so the knowledge is hard to keep track and to keep in the group. But so essentially, the idea was to transfer all kind of the mess we have in the labs. The experiments are done with tape, you know, cables lying all over the place, and trying to put it in a shiny box, hoping obviously that what is in the box works much better than what we have in the lab. That's the goal. So essentially give that to engineers, people who know how to build things in a proper way, in a functional way, in a way which is scalable. So that was the first motivation. And Wazik announced that we have like 7 QPUs that have been sold and in operation. This is actually a massive achievement. When we look at the complexity of operating those machines, the fact that they can be built in Massy or in Canada and shipped to another place on the planet, reassembled and working, to me is absolutely amazing. Second important thing, that was the belief from the very beginning that we needed to explore applications and enhance with the end users. Okay, there is always the belief among physicists. I mean, physicists are a bit arrogant, so they believe they can understand everything and predict everything, and in particular, what those machines could be useful for. And I don't believe this is the physicists who are going to find out what they are useful for. It's by providing those machines to potential end users, them using the machines, feedbacking on us, that we will find the true applications in useful cases of all these machines. So it was very important from the beginning that these applications, even when the machines were not yet ready, were already explored. And so today I just flash a few examples. Wazik mentioned a few other ones, but graph machine learning, financial risk management, solve configuration prediction in drug discovery, smart charging electrical vehicles. So essentially the idea there from the beginning is that take a real life problem and can you put it as a mathematical model that the machine can solve. That was really the key idea, and it's far from being obvious for many problems. So here we are today with what Wazik explained to you. But so what is the future? So of course the future I have no idea, as usual, but you can kind of have a vision and a wish list of where you would like to go. Pascal has demonstrated quantum advantage. So quantum advantage, this is this idea that you can do better than with any known classical simulations today. So it's kind of a moving frontier, but yet it has been demonstrated on academic problems. And so now the true challenge is to extend that, and that's a true challenge for the field, not only for Pascal, with useful end use cases. Second important thing, and that's also a defining moment for Pascal. Pascal has performed, Wazik mentioned that, and we'll hear more later this afternoon, about the fact that Pascal demonstrated, in collaboration with a group at Los Alamos, the first true material science done on QPU. So you just take a piece of material which you can hand in your hand. You put it in a magnetometer, measure its properties, and you compare to the outcome of what the quantum computing computer from Pascal could predict. And you find an excellent agreement between the two. So that's a defining moment because you benchmark your machine against a true material. So that's really something totally amazing, I find. Wazik mentioned it as well. There is the fault-tolerant approach, which is kind of the future of this field in the digital. And already this is an example of a circuit that Pascal is using in order to implement logical qubit and calculation with logical qubits. The road is still long. I mean, it's challenging. We must have more than 10,000 qubits, operating cycle at a millisecond, and fidelities of gates which are kind of very large. But Pascal is really on board to achieve that very rapidly. And actually, in an environment which is more and more competitive, there are more and more companies, more and more announcements done either at the academic level or in those companies. Pascal is uniquely positioned in this competitive environment, thanks to two things, the combination of the R&D and the engineering approach. So that was the trademark from the very beginning and the idea of Pascal. and that gives a computational advantage for the company. The R&D, on top of that, explored now in collaboration between the Institut d'Optique and Pasqal through a joint lab which has been created also with CNRS, which is called Atomic Labs, where we'll explore the further, I mean, beyond the 5 years, if you wish, so that we make sure that we're always on top of things for the, when new ideas, new technologies have to be tested. And with that, I thank you very much for your attention.